Okay, so what we have learned last week is actually we have already know that we have three types of power in the AC systems. We have real power, and then we have Q, which is reactive power, and lastly we have what we call apparent power, S. And the unit is in watt, var, and also VA. Okay, and this is actually the meters, three-phase AC power meters that usually you can actually have it in industry and so on. Okay, so it will display all the informations that for the AC power systems. Okay, so this is an example that we haven't yet test. Okay, we haven't yet we announced that we need when. Okay, there one question before we start. When will announced that we need to back to okay, this one you can actually come back to the campus, but it's actually case by case, because I have I think majority of my students under my supervision academic have already obtained their approval to enter the campus, but it is case by case. It is not what I call, it's not mass, it is not mass approval. Okay, it's case by case depending on the situation and so on. Okay, but the announcement, I don't know, it depends on the school and the university. Okay, because other university I can see that they allow the student to come back to the campus, but for UTM still don't have any announcement. Okay, we have also contacted our deputy chair for academic, Dr. Fendi. He still didn't have any answer because it actually depends on the universities. But you can request, okay? You can request, and the approval is case by case. Okay. So we go back to this our um, example. So calculate the instantaneous power and average power absorbed by this passive linear network. If you have the voltage, okay, and the current is this one. For example, maybe this is the voltage. This is the unknown elements that the voltage across is these values, okay, and the current that flows inside that element is these equations. So calculate what is the instantaneous power, average power absorbed by the passive element. Okay, so we know that AC power, we have instantaneous power, which is P plus, what is the equation? Okay, this one, P plus P cos 2 omega T minus Q sine 2 omega T. Okay, P plus P cos 2 omega T minus Q sine 2 omega T. Okay, so right now we need to find P and also your Q. So your P is actually Vm Im over 2 cos theta V minus theta I is actually, okay, the angle between the different angle between voltage and the current, while Q is actually Vm Im over 2 sine the different angle between voltage and also the current. But right now, as you can see, and referring back to the circuit theory, for an AC waveform, you cannot directly use this information given directly, because if you want to compare the waveform, okay, both AC waveform, you need to ensure there are two conditions so that you are allowed to compare this what you call, so sorry, there are three condition. Okay, they if these condition are what you call met, then you can actually proceed with the analysis, comparing these two waveforms. The first one, it need to be in a same function. So right now, same function. The second one need to be same frequency. And the last one, same what we call sign. Okay, so if the voltage is one is a positive and then current is one is negative, you cannot compare, you cannot analyze. Okay, you need to ensure these three conditions are met. So right now the second condition are met because this is your omega. So the omega is actually same, meaning that because omega we know is 2 pi f, right? So meaning that if omega is the same, meaning that the frequency is same. The only uh, requirement that need to be met is actually V is actually in the cos function, but the current is sine function. So what you need to do first is to convert this sine function into a cos function. Then you can compare. Okay. So right now, these two elements are met. We have same frequency and we have the same sign. The only element is actually need to be in a same function. So this, for example, for the current, I want to convert this current function into a cos function. So you need to go back to the fundamental of mathematics in trigonometrics. Okay, so sometimes it's quite confusing and it's quite difficult to memorize. What I do is actually I just memorize these tips. Okay, so how to convert from sine to cos. So for example, we have this sine and then this is cos and then this is negative sine and this is negative cos. For example, if I want to change the sign, okay, not sin, okay, sin is a dosa. So we need to change this sine function into cos function. So we need to have negative 90 degrees. So meaning that sine omega t, if you write in cos function, it become cos omega t minus 90 degrees. So this one, I is become 15 cos 10 t plus 60 minus 90 degrees. So this one will become 15 cos 10t minus 30 degrees. So, okay, so in a polar form, I can write down my V is equal to 80 with an angle of 20 degrees and my current is 15 with an angle of negative 30 degrees. So this one is your theta V and this one is your theta I. Okay, so P is equals to 80, 15. We assume this is actually maximum value, okay? Maximum value. Okay, over 2 cos theta V minus theta I. So 20 minus 30 degrees. So what is the answer? Okay. I need to to discard or to keep. Okay, hold on. I need to. Can someone calculate for me? Oops, sorry. I have with this one. Okay, just to transform this one to this one. Okay. Oops, sorry. Okay. So what is your P? Can someone? So 80 multiplied with 15 over 2 cos theta V. Theta V is 20 minus 30 degrees. So calculator. So I have with me right now the calculator. So 80. Oh, sorry, I cannot see your chat. So sorry. 38.385.67. Okay, thank you very much. Okay, and then Q. So what is your Q? So your Q is 80 multiplied with 15 over 2 sine 20 minus 30 degrees. So this one should be okay, 80. It should be why my keyboard didn't function. So 80. Yeah, okay, 80 multiply with 15 over 2. Oops, why? 80 multiply with 15 over 2, right? And then multiply with sine 50 for 159.63. Okay. Okay, so that is your Q. So actually, okay, so we have already obtained your P. This is your questions. So average power. So this is the element will absorb 385.67. So your instantaneous power is actually P plus P cos 2 omega t minus Q sine 2 omega t. So you just write down 385.67 plus 385.67 cos 2, and your omega is 10, right? So 20 t, okay, minus 459.6 sine 20 t. So that is your instantaneous power. Okay. So let's go back to the PowerPoint. Okay. Second example. Oh, this is calculator. Okay, the calculator is already. Oh. Okay. Hold on. Because they are. You can turn on the microphone if you want. Because revise a bit on how to convert the volt current into a polar form using calculator or what? Are you mentioning about using the calculator or just from the time domain into a polar form? Is it using calculator? Okay, from time domain. Okay. So, okay. For example, if I have my voltage, okay. For example, this one, 80 cos 10t plus 20 degrees. Okay, so for the polar form, what you need to do is actually the polar is requires the amplitude and also the phasor. This is what you call phasor. This is your phasor. Okay, your phase. So your amplitude is 80 and your phase is 20 degrees. So it's simply like that. But you need to ensure that, for example, if you want to multiply the voltage and current, you cannot multiply, for example, if I, okay, oops, sorry. Oh, I cannot. For example, if I have this, my VT is 10 cos omega t plus 0 degrees. And my current is 5 sine omega t plus 50 degrees. Okay. I cannot, for example, if you want to change the phasor, okay, so it become this one and this one is 50 degrees. Okay. And then you need to multiply. For example, P, V multiply with I. V capital and I capital is actually referring to phasor. Okay. So 10 degrees multiply with 50 degrees. So the answer is this one. Magnitude multiply with magnitude. And the angle is, you need to just add up 50 plus 0. So 50. But this one is actually wrong. This answer is wrong. Why? Because if you want to proceed with a phasor, we want to convert into a phasor, you need to make sure that before you convert, the time domain of the voltage and current must fulfill the all the requirement. The three requirement there must be same frequency. In this one is actually same omega. You need to have a same function. So if voltage is cos, the current must be in cos. Okay, must be in the same function. And the last one is the sign must be same. So both must be positive or both must be negative. So this one need to be fulfilled first before you proceed with conversion of the phasor. Because if you do like this, for example, 10 cos, okay, you just convert into a phasor, 10 with an angle of 0, and current is 5 sine, and then you just convert by 5 equals 5 with angle 50, so, and then you multiply. So this is wrong. This is totally wrong. Okay, you cannot simply convert this one. You need to change sine into cos. For example, so 5 sine into cos, so it become cos omega t plus 50 minus 90 degrees. So 5 with an angle of negative 40 degrees. So this is correct. So right now, 5 current function and voltage are in the same function. So you can proceed with analysis using phasor domain. Okay, so when you want to multiply the voltage and current, then you will receive 10 angle 0 multiply with 5 with an angle negative 40 degrees. So this one is 50 negative 40 degrees. Then this is correct. The answer is correct. Okay. Did I answering your questions? Okay, I hope so. Oh, the sign. The sign is actually the what you call the tanda tu lah. Some even it is positive or is it negative? Because sometimes it given this one like this, negative. This one positive. Okay, so the voltage is negative 10 and the current is positive 5. So you need to convert because this one negative 10 is actually negative 10 cos omega t. This one is actually 10 multiplied with negative cos actually. Okay, you need to convert into positive cos. Because negative cos is not the same with negative cos. Because how to convert this one is actually by using this plane. Okay, sine, negative sine, cos, negative cos. So how to convert into negative cos to cos is actually by using this one, negative 180 degrees. So meaning that negative cos omega t, when you want to write down into a positive cos, it will become cos omega t plus 180 degrees. Sorry, negative. Okay, negative 180 degrees. Okay, the units for the instantaneous power is still watt. W-A-T-T. Okay. The still because this is actually power. Okay, watt. So the unit is watt for the instantaneous power. Oh, I see. Sorry. The instantaneous power, I need to refer back because as you can see, yes, okay. So the instantaneous power is still what? The unit is what? Because this Q is actually just a constant. Okay, just a constant. There is no what you call units. But when you talk about average power, then it is what? Reactive power. Q is actually var. Okay. P and Q at this equation of instantaneous power is just a constant. Okay, it's just a constant. Oh, this one. I hope I can erase this back. Okay. Okay, let's proceed with the second example. Any question? Okay. Okay, so so we have a impedance which is 20 negative 20 negative 22 degrees. So this is your impedance. From looking at this impedance, what you say about this impedance? Is it resistor, pure resistor, or is it capacitive? Is it R, RC, or RL based on this impedance? Can someone? Based on the impedance. Is it R, RC, or RL? It's surely not R lah. Okay. Based on the impedance. Yes, RC. Okay. Because RC. Because do you know when for the RC, the impedance is R minus JXC. So this minus will determine your angle. Okay. Okay. So if the inductor, if is L actually RL, then you will have R plus JXL. Okay. So this is a capacitive. Okay. So the load is a capacitive load and the current that draws into the load is 10 with an angle of 30 ampere. Okay, so right now, find the average power delivered to the impedance. So right now, the current, I can say that this is R and capacitor. Okay, so this is actually, we have the current going is 10, 30 degrees. Okay, so right now, you want to find the average power. So how to find the average power? First, what you need to do is actually to obtain the voltage drop across the impedance. Okay, the voltage drop. So the voltage, so it's very easy to calculate by using a phasor domain. Okay, so this so 10, okay, with an angle of 30 degrees, multiply with the impedance 20 angle negative 22. So you will have this one, I think if I calculate 200 with an angle of 88 degrees. Okay, 8 degrees. So that is your voltage. Okay, so right now I have already obtained my voltage magnitude. This is your theta V. This is your current, and this is your theta I. Okay, so you have all the information. So your average power is just simply by using the equation. Okay, so your VM is a 200 multiply with 10 over 2 cos theta V minus theta I, 8 degrees minus 30 degrees. So you will obtain your values of power. Okay, discard this one. Oh, I don't have with me my calculator, so can someone just calculate it for me? Where is my scientific calculator? Okay. Sorry. P is equals to, oh, this one got a background. Okay. What is your V? Is 200 multiply with 10 over 2 cos 8 degrees minus what is your angle? The current 30. Okay. Okay. So 200, sorry. 100 multiply with 10 over 2, then multiply with cos negative 22. 97. Is it? Oh, 927. Okay, good. 927 watt. And the reactive power, so simply just 200 multiply with 10 over 2 sine negative 22 degrees. So you should get the answer lah. So it's very straightforward, okay? Okay. Okay, let's move on. Oh, this exercise. So this exercise is quite complicated, but it's worth to try because it will related to the next topic. Okay. So exercise. So this one. Okay, this one. Okay. Okay. So you can have this one. Try 5 minutes. Then we will proceed with the discussion on the solution. Okay. So 5 minutes. So if you want to go to the toilet first, okay. So if you want to try first, okay. So after this, we will discuss. Oh, I mute. Okay, can you hear me? Okay. So actually the solution is quite long. and I think it's not appropriate to fully discuss uh, the solution. So what I will do is actually I will share the solution with you in the WhatsApp group. And but at the same time, for this one, I think I will just show what is the steps and what is the correct way on how to solve this one. Okay, so let's look at the question first. So consider the circuit below. So it is given in a phasor, already phasor, 120 volt, and this is maximum values, and with an angle of 0 degrees, and the frequency of the circuit, the overall circuit, is 50 hertz. So meaning that all the components here are working on 50 hertz frequencies. Okay. Find the average power absorbed by the load before the switch is closed. So as you can see, we have RL load here in series and a capacitor that connected in parallel. But we have a switch here. Okay, so the switch is actually in initial condition is open, meaning that the only circuit that operated is only RL load only. Okay, while the capacitor is open circuit. Okay, so the first question, find the average power, meaning that average power before the switch is closed, meaning that the average power absorbed by this impedance. Okay, and then the second question, find the reactive Q in the system before the switch is closed. So meaning that the impedance, so meaning that the first two questions is actually the P and also the Q. Okay, for this impedance. And lastly, what is the reactive power supplied by the capacitor after the switch is closed? So the interesting part is actually on the third questions. Okay, so what you need to do is first you need to convert all the circuit element into a phasor. So right now we have already know that the frequency is 50 hertz. Okay, so you need to convert Henry inductor into a reactance. We know that your reactance XL is, your X is omega L, okay, 2 pi FL. So you need to 2 pi multiply with 50 hertz multiply with the Henry units. So you will obtain your reactance for the inductance is J50. So this is your total impedance here. Okay, and then convert into a phasor. I hope you know how to convert this one. Okay, so what you need to do is just I show you, maybe you forget, okay, but you should already know. So what you need to do is just goes to the mode and click mode complex 2. Okay, so right now you are in a complex mode. Okay, so what you need to do is just 60 the real part plus the imaginary part. So the imaginary part you just click 50, sorry, 50 shift I. Okay, so this one is your complex numbers in rectangular form. So how to convert into a phasor form is actually just shift plus. Okay, shift plus. So it will have these notifications. So it is converting to phasor form. Just click equal. So it will give you the values. This one is the magnitude. And then if you want to go for the angle, just shift equal. So it will give you the values of the angle. Okay, so this is the magnitude, and to get the angle, shift equal, so it will give you the values of the angle. Okay, so right now we have, from this we will obtain the current. So the current is 1.53 with an angle of negative 39.8. So hence the average power is actually VMIM over 2 cos theta V minus theta I. So just use the magnitude, 120 multiplied with 1.53 over 2 cos with an angle difference. Okay, so you will obtain the angle of the voltage is 0, while the angle of the current is negative 39.8. So theta V minus theta I So, and then you will obtain your power is equals to 70.5 watt. Okay, so that is your average power. The second question is about reactive power. So the reactive power is Vm over 2 sine theta V minus theta I, where you have already obtained Vm and Im and theta V and theta I. So you just proceed with the equations. You will obtain that your Q is 58.7 var. Okay, this Q is positive. Q is positive because your inductor, because your load is inductor, because you are inductive load. Okay, so that's why your Q is positive. If your Q is if your load is consisted of a capacitor, you will see that your Q will become negative. Okay, because of this angle actually. Okay, automatically negative based on the calculation. But right now, based on the calculation here, you will receive a positive Q, meaning that it is actually true. Your calculation is true because your load is inductive load. Okay. Okay, so find the reactive power supplied by the capacitor after the switch is closed. Oh, I put like this. I think this one is wrong. This one is totally wrong. So my mistake. So this is not the answer. This is not the solution. What you need to do is okay. So this one is totally wrong. Totally wrong. This one. So I need to. This one is wrong. Okay. Sorry. So this one is wrong. So I need to show again. So this one you have 120 volt with an angle 0. So right now your what is the value of the capacitor? Okay, negative 144.7. Okay. So your capacitor is 144.7. This one is actually you need to convert, okay? Because we know XC is negative J 1 over omega C. Okay? So negative J 1 over 2 pi 50 multiply with your capacitor. So you will obtain negative J 144.7 ohm. Okay. And then still you will have the resistor and also inductor. Okay, so your resistor 60 and your inductor is okay. So you need to simplify this circuit actually. Okay. Simplify the circuit. This one should be R plus JXL parallel with XC. Okay. Okay, sorry. So meaning that you need to simplify this one. Okay. And then get this one. Okay, I don't have the answer right now because it requires a lot of calculation here. Okay, so or can someone just calculate for me? It's quite what I call tedious work. Okay, but never mind. I think I will continue this without completing this solution. Okay. Okay, I will give you the answer for it. Okay. Stop sharing and then Are you with me right now? Hope you are still with me. Okay. So find reactive power. This one is not solved yet. Okay, but I will give you. So actually, what we do is actually here we have the Q is actually this one is actually will produce positive Q. Okay, and then this one will produce negative Q, and then this one will produce P. Okay, so the total Q, okay, the Q total is actually the summation of all Q of the elements. So right now, the elements uh, that can produce Q is only capacitor and also inductor. So you will have this one negative QC, okay, plus QL actually. This one should be 0, okay? While for the power, is actually all the summation of the element that can produce, that is actually absorb the power. So right now, as you can see, only resistor that actually absorb P. Okay, so this should be equal to 0. So actually, the total power inside the inside the circuit must equal to 0. So this one I will explain later lah, because you don't have, because we cannot solve this one because of the time constraint. So that's why I think you don't have what you call some insight what should happen actually. But it is actually what the power factor correction. If you go to Giant, Tesco and so on, I think lately dah tak ada dah. But I think the previous years, kan, when you say that sometimes when you go with your family, so sometimes people approach you, so to reduce the bills and so on, right? So they introduce some black box. So by installing that box, it will reduce the bills. So actually, what is do is actually the black box is just a capacitor. That inside the box is just a capacitor, because this capacitor will reduce the reactive, because we know that our load is a inductive load. Okay, it will produce positive Q. Okay, so to minimize the Q, so we need to introduce the what you call its negative Q. So the negative Q can be only obtained by installing capacitor inside your house. So by reducing Q, okay, positive, this one negative Q, so it will actually reduce the consumption of energy that you take from the TNB. That one is actually what we call the power factor correction. Okay, this is very simple approach in um, reducing the electrical bills. Okay, by reducing the Q. Okay, this Q is inductor. We cannot what we call what we call this inductor is actually is very easy to create, even though we don't want the inductor, but it is very easy because the inductor basic is actually the solenoid. Okay, so everything, the wires, okay, you have cables, so when the current is going flow inside the cable, it will generate some magnetic around the cables. This magnetic, when actually you have a lot of wires, okay, jumping, mix, okay, so this magnetic will actually mix and it will produce some mutual inductance. So mutual inductance, mutual inductance, and then it will create Q, okay, positive Q. So that's why we have Q. Uh, we have we have a Q in our home. Okay, so actually the power factor correction is actually legal. It's not illegal. It's actually legal because it will save the TNB actually. The TNB will be at the positive side. It will be because this is legal, and then the TNB, or actually all the factories, industry, they can install this capacitor banks, okay, capacitor bank to correct their power factors. Because if you have low power factors, it will deteriorate the whole power system grid. Okay, the power quality of the grid of the TNB will be very, very bad, and it will cause the TNB some damage in terms of the cables and so on. Because power factors, if you're very low, it has introduced some kind of what you call harmonics and so on, and the current is actually very, very high. Okay, the current that actually in the transmission line will become very, very high because of this harmonics, and this harmonics is because of the power factors. So the TNB is actually this is legal. Okay. So the TNB don't provide power factor correction. It's actually there is a regulation. Only the TNB is actually can provide the power before entering the meter. So after the meters is actually responsible of the customer. Okay. So the TNB only their responsibility is before the meter. After the meter is up to the customer on how he use the electricity, how he want to reduce the electricity and so on. Okay. Okay, so I think we have finished on the power. So let's go to the next topic. This one summary, I think you can I think just a very short one. So this one okay and this is okay, but for the inductor, this is a short circuit. Okay, in the DC analysis, it is short circuit. Only the AC analysis is available. For the DC analysis, for the capacitor is actually open circuit. Okay, only AC analysis is this one. Okay, and the power formula for DC is very simple. It's actually just because only resistor is available for the DC. Inductor and capacitor is not available for DC analysis because capacitor is open circuit, inductor is short circuit, so only R. So you can just this one or I square R. But for the AC analysis, since you have inductor and capacitor, so your power is very complicated. So you have three type of different power, P, Q, and also S. Okay. So this one. Okay, this one. Okay, part 2, which is the effective or RMS value. So what is the RMS? So usually AC power system, you always have heard about RMS, 240 volt RMS, 100 RMS, and so on. So what is actually RMS? So actually in the AC system, so it is required some what you call effective value to calculate the power absorbed by the load. For example, you have this kind of circuit, AC circuit. You have a load. So you want to measure what is the current that produce the power. For example, that equals to the DC circuit. Okay, because this is periodic and so on. So for example, you want to see what is the current, what should be the current value to produce the same power. For example, if the circuit of the DC produce this load is actually absorbing 200 watt. Okay, what is the value of the current that can produce the same 200 watt? Okay, so they have shown here that this effective current. Okay, so for example, to calculate the power that for the AC circuit, okay, so we know that the power is actually for the AC circuit is VT multiplied with IT, or you can also write down as IT square multiplied with R, right? Right? I square multiplied with R. So this is also P. But what is the P average? So to get the P average, we know that I, so you need to integrate the values of the current. So we know that the current is periodic. So to get the average current values, so you need to integrate. So this is your current. The integration to get the current average. Okay, this one. And R, you know, is actually a constant. So you can take out the R, so you have R over T. Okay, and then integrate from 0 to T, I square. So this is IT actually. Okay, so this is the power that produce the same power of the DC circuit. While for the DC circuit, is very straightforward. I, which is a DC current, I square R. So right now, what is the current that can produce the same power of the DC circuit? Okay, so from this one, we can see that your I effective is equals to, I effective square is equals to 1 over T from 0 to T, I T square, which is, this one is your IRMS. Okay, which is, after that, we finally obtain that the current that produce the same DC power can be computed as by using this equation. This is from the DC current. And this is the IRMS, is actually the AC current that produce the same amount of power for the DC circuit. Okay, so this is the equation to get the IRMS. Okay, and same to get the VRMS, the voltage that give the same DC power equivalent output. So the VRMS also can be obtained using this equation. The same equation, you only need to replace I with the voltage equation. Okay, and by solving this equation, finally you will obtain that the current effective of the AC that produce the same power of the DC circuit, which is I RMS, is equals to I maximum over square root 2. The same goes to the voltage. So the VRMS is equals to VM over square root 2. So this indicates that the effective value is actually the effective value of the current and the voltage that produce the same amount of DC power is actually the square root of the mean or the average of the square of the periodic signals. Oh, quite long, this sentence. Okay, so because of that, of the root means of the square root, so the effective value is also known as a root mean square. So this is actually the origin of the RMS, root mean square, because it comes from the square root. Okay, so the effective value is come from the square root, so that's why root mean square, or sometimes just a short form is RMS. So for any periodic function, periodic function, is it in a sine or cos function, the RMS value can be simplified as the value of the maximum value of the waveform over its square root 2. Any waveform, but the waveform must be sinusoidal waveform. Okay, so that is the origin of the RMS. So we will always use these RMS values in our future calculation, because this is the standard right now. Okay, so we are using RMS values, not maximum values. Okay, so I want to connect the RMS values with the power calculation. Okay, previously we know that for the average power calculation, the equation is Vm Im cos theta V minus theta I. Right now, since we are using, after this we are using RMS, so we need to convert this equation into RMS function. So we know that how to convert into this one. Okay, so we know that actually this VRMS IRMS is actually VM over square root 2 multiply with IM square root 2 cos theta V minus theta I, right? And we know that this one is actually VM IM. So square root 2 multiply with square root 2 is 2. So that's why. So rather than we use this one, we can, if you are using RMS and IRMS, just use this equation. VRMS multiply with IRMS cos theta V minus theta I. Okay. If you are using maximum values, please use this equation. But if you are using RMS and IRMS, use this equation. Okay. But this equation is actually interchangeable. You can either change into using VM or RMS. Okay. So I hope you understand this one. If you are using VMIM, please use this equation. You need to divide it by 2. But if your voltage and current are already in RMS, so use the second equation. Okay. And also goes for the, so since this is actually the original equations, okay, so we can also use the average power calculation using this equation. So instead of using IM, so you are actually I square RMS R and V square RMS over R to compute your P, okay, average power. Same with the reactive power. So if you are using your voltage and current are in a maximum value, so use this first equation. And if you are already in a V RMS value, so you're using this second equation. Okay. And this is for the Q, for the inductive load. Okay, positive Q, okay. So I square XL or V square XL. And also for the QC is a negative I square RMS XC, or you can also use negative V square RMS over XC. Okay. So power engineers conventionally say voltage and current in RMS. So that's why we are using the RMS. Okay. So for example, our socket right now in our home appliance, 240 volt. That one is actually RMS values, not peak values. Okay, 240 volt RMS, where the peak value is actually 339 because you just multiply 240 volt. So VM over square root 2. So VM is equal to 339.4. Okay. So as you can see, this is the comparison between the RMS value. So RMS value is actually effective values. It's actually like DC values lah. Okay. This is 240 volt RMS. And as you can see, this is the sinusoidal waveform where the P max is actually referring to the maximum value of the sinusoidal. But for power system, electrical engineering in AC system, we are normally use RMS. Okay, I think that's all. I think you can proceed with this example. This example is actually the same example of example 2 the previously, but right now it using the power calculation using RMS. Okay, but actually you will get the same answer. Okay, just use the RMS equation only. Okay, and for example 4, you can example 4. So example 4 will be discussed on our next class. Okay, example 4. But just to let you know that for example for our next class, sorry, not clear about the difference between normal current and RMS current. So normal current, what you mean by normal current? Because in DC, if a DC circuit, so that DC current is your normal current. Okay. The RMS current is actually referring to the current of the AC circuit that will produce the same amount of power of the load. Okay, the amount of current that is actually equivalent to the DC current. Okay, because right now AC is a periodic, so we want to see what is actually the effective values of that AC current that will produce the same amount of power when for the DC circuit. So DC circuit is actually just a VI, right? I is a DC current, a constant. So very easy to calculate the I. So but right now for the AC is a periodic. So we want to see what is the value of the current that is actually same with the DC current, that we produce the same amount of power. Okay. Okay. So for this one, our next class will be on Wednesday. So I need to send my daughter for the second dose vaccine. So the appointment is in the morning sessions, and I think around 10 a.m. So our class is 11 a.m. So I think it's not possible for me to get in time. So what I will do, so I will pre-recorded this example for solutions and also for our next topics. Okay, so I hope you can watch the YouTube video. I will upload the YouTube video. I will give the link after this. So class, we don't have class on our next Wednesday. Okay, so we meet again next week inshallah for the class. Okay, I think that's all from me. Any questions? So I just go fast on the RMS because it is very simple, straightforward. So just because one of your friends said, ask me, start at 8 p.m. Okay, so for test 1 and test 2. For test 1, do you mean test 1? For test 1 and test 2, we will try because this involve a lot of a big group of students. I need to ask the coordinator and all the lecturers. Okay, so because I don't know why we start at 9 p.m. Maybe because of the time constraint between is very short, I think. So maybe that's why. But if need to be agreed by other sections also. The working step, I will share with you. I will share in the WhatsApp group. But it's very important that you try first, and then after that you can you can look at the steps. Okay, because the step is quite simple, it's quite straightforward, but you need to try first so that you will be familiarized. Okay. Okay, thank you very much for your attention. Okay, so but this is very important, the RMS. Okay, the RMS is very important. So I hope you understand the RMS. So RMS is actually for the current or the voltage that produce the same. Actually, we treat this RMS current and RMS voltage as a DC current and AC and the DC voltage lah, like that. We just treat like that because AC circuit is a periodic. So how we want to treat this AC as a DC circuit? Okay. So that is actually the concept behind the RMS. Okay. So thank you very much. So we stop here. So see you next week. Yeah. Assalamualaikum. Have a very good day.
Waalaikumsalam. Thank you, Doktor.
Thank you, Doctor.
Okay.
Thank you, Dr.